I'll give a brief intro to AI and machine learning, very high-level perspective. And you can think about AI and machine learning, as well as other systems, as algorithms. So any type of algorithmic decision making, it could be an AI system, could be machine learning, or could be just a person across the computer, give you some decision. Think about this as this person is following an algorithm. This person is following a rule-based system. And you are just trying to understand what's going on. So I'll just give you a brief intro to that, and I'll talk about the key components of algorithm impact assessment, and then I'll focus on the three main ones: explainability, fairness, and robustness. So just focus on the introduction to AI and machine learning, just the principles and goals, ways to learn in a nutshell. I'll talk about supervised learning, which is the key mode of learning that has been the most successful. And most of the system we are kind of dealing on a day-to-day basis, they are supervised learning type of systems. How do we evaluate them, the typical modeling pipeline, and when learning works and fails. So there's this nice diagram, which you have artificial intelligence as this overarching concept that it basically programs with the ability to learn and reason like humans. And this is kind of the goal. That's where we're heading to. But for a long time, we were fixated with this idea, and we couldn't develop much. And I think in the last 50 years, even last 40 years, people decided to say, okay, maybe we just, instead of trying to create systems that reason like humans, maybe we just, that's below human level, and let's focus on systems that could solve a particular problem, like object recognition, like credit scoring people, things like that. That just a small, narrow task that the system would be able to do, and hopefully it would be able to do better than a human. So, and then, in a way, the most successful of all approaches was machine learning. There was some other type of learning that wasn't so successful, which like the symbolic type of adventures that the AI researchers did in the 70s. It was too difficult. It was kind of hard coding rules. It didn't work out very well, wasn't scalable. And in a way, machine learning was the most successful, which basically algorithm is that the ability to learn without it being explicitly programmed. So you just need data. And as long as you have a loads amount of data, your algorithm gets better. Instead of you trying to translate a human knowledge into a system, you just collect data and then use the data to learn the rules of the system. And most of the things you see doing by the Google people and the DeepMinds and Facebook and so on, they are in this deep learning layer, which is just a different way for you to train your models. And they are basically neural networks, or models that are stacked on top of each other. But I guess 90% of the stuff that we see out there that we think are smart are in machine learning. And some of them are in deep learning, some of them are just using random forests or some other tool. And there's this nice quote from Zuckerberg, and interesting one. Whenever I hear people say AI is going to hurt people in the future, I think, yeah, technology can generally always be used for good and bad, and you need to be careful about how you build it. It's a bit of a shame anyway, but it's an interesting quote. And I think it's quite an old one. Maybe he has changed his mind in the last few years, hopefully. Zainab has showed this slide before, but the difference between traditional programming and machine learning is traditional programming is you give the program, you give the data, give to the computer generates an output. Machine learning is you give an output, you give some data, and then the machine will learn the program for you. And on a very simplistic term, in the traditional programming way, you give the data, let's say 2 and 2, and the program is plus. And you ask the computer, what's the result of 2 plus 2? And the program says 4. That's what the computer would do. In a machine learning sense is you give the data, 2 and 2, and you give the output, 4. And then you ask the computer, what is the program that picking 2, and 2 transforms into 4. And the computer would say maybe plus, maybe times. So that's where it starts to be a little bit difficult, which is the same problem as we see around here, which is the machine will come up with an answer that looks reasonable in the principle, but if you, let's suppose we say times, next time that you say 3 and 3, it's going to say 9 instead of being 6. So that's why you need a lot of data, so the machine can avoid these mistakes, hopefully. In a way, both are algorithms, but on a very distinctive way. In traditional programming, often the system is static, it's rule-based, and it tends to be easier to verify because it was coded by the humans. In machine learning, the system is dynamic because with new data, the system changes. It's functional, so instead of using if and else rules, you're using now plus, minus, exponential functions, hyperbolic functions, and so on. And it tends to be harder to verify, but you can verify. That's the most important thing. So there are different ways for you to learn something. You can learn using what we call supervised learning. There's a teacher in the room, and the teacher tells you, okay, here are some news, and some of these news are positive, and some of these news are negative. So the teacher tells you what is positive and what is negative, and then the machine tries to learn that given new data, what would be positive news and what would be negative news. So without now a human intervention in the loop, the machine will just select it for you. But there is someone from the beginning labeling things as positive and negative. And supervised learning is a little bit different. You just start with the news, and then the machine will try to learn a structure that is presented in the news. How can I separate the news into topics, for instance? Are these news from politics or war or Trump or some other topic? So the machine will try to attempt to build that, but without much human input in the middle. Reinforcement learning is, you can think about the news, which we were talking before, as giving you an idea about the state of the world. And giving a state of the world, you have this machine we call learner, and the learner tries to say, okay, the state of the world is like this. That might be a worthwhile action for us to employ in this state of the world. And then you apply this action, then comes the environment, which is the word, and the word gives you a new state and also a reward. So how much your action was worth. And then you use these new inputs so the machine can decide what's a new action now. And in a way, reinforcement learning is what I would say most of the DeepMind type of success has been. So most of the stuff you see in the middle, like AlphaZero, there's now the Alpha Star, and there was I think that was OpenAI with Dota. So most of the success in reinforcement learning has been, you have a virtual environment, which there is a game, and the game has some rules, and then you can play zillions of times. So just some formal definition. So supervised learning is, you have a set of inputs, you have some output variable, and then you have a lot of samples from your words, and then you create a data set, which is basically inputs and outputs, a lot of them. And your goal is to find this function here in the middle. So it's a mathematical function that links inputs to outputs as best as you can. And there's two main types of supervised learning. One is classification, and another one is regression. And I'm just going to show you an example. So classification is, if you're playing with object recognition, you're asking what is in the image. So you give an image, let's say in this case of a dog, and you ask yourself what is in the image, and the system would tell you, okay, that's a dog. So you're labeling things. In regression, you are, for instance, asking where is in the image. because what you want to do is to find the localization of the object. So regression is more about numbers, real numbers, so values in an interval, whilst classification is that a dog, is that a cat, is that a person? So in terms of mathematical structure, it's a little bit different, but in essence, they're in the same umbrella of supervised learning. But for object recognition, classification would mean what, regression would mean where is the image. And there's a lot of success recently on, particularly for self-driving cars, on not only identifying the people in the street or the objects in the street, but where they are located. And that's quite important. And it's the funny thing about humans, we do these two tasks at the same time, right? When I'm looking at you, I know who you are and what's the location you are. And there's like this model inside your brain that maps the whole environment. That's the funny thing. So there's just a simple example. There's a data set, famous. So if you're playing with machine learning, there's a data set called Titanic disaster data set. It's basically the records of the people who survived in the Titanic disaster. And it's a big data set. There's a lot of other characteristics. But let's suppose you pick 80% of the data to train a model. And in this case, it's this nice decision tree. This model was basically built from the data. There was no hard-encoded rules. So the model learned what would be a nice decision tree to predict if someone survived or not survived in the Titanic disaster. And the first interesting thing is the gender male? If no, has survived, definitely. If he has, then it's a little bit complicated because could be, could not be. That's one of the interesting models because it's quite explainable. You can just look to the model structure and come up with some rules. If you go very deep in the decision tree, then it does not become explainable anymore. Decision tree with, I don't know, 10 levels, like impossible to understand. But with 3 levels, 2, that's kind of enough. And let's suppose you pick this decision tree and then you show new data to it, some data that you have rolled out. And here's the new data. So now you know the gender, the age, and the number of siblings this person had during the Titanic journey. This person has survived. But the model, if you go through all the steps, said no. So that was a mistake. So the person has survived, but the model said no. And there's another case which is a woman here. She has survived, she has died, but the model said yes, she survived. And you can create a nice confusion matrix like this, which tells you observation yes, prediction yes, and you can just count the number of yes and no's and fill these boxes over here. With this confusion matrix is a way to summarize the model performance. But that's not the solution. The solution is which metric you're going to use to evaluate the model. And that's where the mathematical problems kicks in, which is what sort of metric you're going to ask the data scientists to use to evaluate how good is a model compared to another model. And I learned in the schools 10 years ago when I did my data science course that we should just look into maybe accuracy, precision, sometimes F1 score, sometimes area under the curve, and that's it. So we didn't learn about fairness, we didn't learn about robustness, we didn't learn about explainability. Just look into these numbers. If they look good, that's it. Just go to the next task. And one of the key problems tends to be when you summarize everything into a number, you stop thinking about the model and you stop thinking about how good the model is. And that's a big problem of the data scientist profession in a way. It's like we are really going for the numbers and not thinking about how the model should look like and what's the good model. And it's a bit of a shame. And I think it's still like this these days, unfortunately. Because we are always thinking about what is the next model? What is the new deep learning that we can use to solve this problem? Instead of thinking, what are my variables? Does this model make sense or doesn't make sense? So that's usually the modeling pipeline. I'm showing you this because this will be very useful later on, so you can understand where you should do the impact assessment on your algorithm. So everything starts from the data, and how do you collect the data, how you fetch the data. That's the most important part. After that, these 4 steps over here is kind of automated in a way. One is the pre-processing and feature engineering. And people really spend a lot of time doing this step, thinking about the features, thinking about how we can create new ones, just to improve the model. Because that's more or less the mapping is. There's a key problem there is depending on how you manufacture your features, they just become not interpretable anymore. So if you apply a lot of completely hard transformations, they just lost their semantic value, and then the explainability goes out of the window out of that. Model selection, very important, and usually compared to statisticians, machine learning scientists tends to take a more defensive approach there, which is we don't think that's the right model. We say we don't know what the right model is, let's try 20 different models and let's see which one works better. That's very defensive, but at the same time a little bit complicated, because you say, yeah, I'm not sure, let's just try everything and see how it goes. And that's probably one of the ethos, in a way, of the data science. Like you move fast and you shouldn't break things, but you end up breaking things because you are trying so much stuff and you use what works. Then you do some post-processing, you try to report what is matter, what doesn't matter, and then you productionize and deploy. And that usually is the most hard part, which is, okay, you made this beautiful model, how can you put this in production and deploy? That takes a lot of time, but that's very important. If you want to do some assessment as a potential AI assessment analyst or something like that, I would encourage you to use, for you to understand more the system. Let's suppose you are an outsider and you're going there to do some auditing, to ask the data scientist or someone who designed the system to fill some canvas, and there's the machine learning canvas, which gives you an idea of what are the system's purpose, what are the inputs variable, output variable, what the system is doing, what was the type of model validation that was used, and so on. And it gives you a nice picture, because you can just look into this canvas, and you have a good picture of what's going on inside the system. So if you don't know the system, just ask data science to fill this. It's very quick. We all love Canvas, so he wouldn't feel bothered about filling this canvas for you, so that's fine. Instead of you giving them a form in the Word and you have to fill. Give them a canvas, they're probably going to be happier to fill for you. Just to finalize these initial parts, there are some cases when learning works and fails. Learning works when you are happy with your Spotify discover, when you're getting new, nice musics that you haven't thought about before, and you give a nice quotation like, after I received several excellent playlists in a row, I couldn't stop thinking about how Spotify had figured me out. That was quite an astonishing quote. But at the same time, sometimes profiling, which is this type of stuff that Spotify is doing with you, is profiling you. Sometimes profiling doesn't work very well, which is the compass case, which Simon has brought in. And we can clearly see the problem here. The problem is basically race, and race is coming from some other variable. Translation is also very important, and it has enabled a lot of business and people traveling across the globe to be able to communicate. And it works really well. Where's the train station? Donde está la estación de tren? It works beautifully. But at the same time, as Zenip has brought in, there is some issues there. And you can argue that's probably a problem of interface, but I should have fixed the problem of interface in the first case, instead of just relying the system to work by itself. And I think, yeah, that's finally the last one is self-driving cars. Very useful. You can see here there's a car and where at the same time. It's quite useful. And there's like, there's a car over here with a probability there's a car. And it's probably better than me, I think. It's covering cars. And they like to detect people too. Quite good. But then you have facial recognition London, staggering inaccurate. So you have two words happening. And that's really a clear problem for robustness. You know, sometimes the system works really well. Sometimes the system doesn't work really well. And if the system doesn't work, don't deploy the system. That's probably the first rule. And don't try to put the system in the street, because then you have staggering inaccurate predictions. People are being put on trial or taken to the police department for something they shouldn't be taken. Yeah. So there's some books and some material. This slides are online. I can give you the address later on. And I think probably going to circulate as well via emails. Yeah, it is all in Zenodo. So you can just download it. Sorry for not bringing it printable. It's like nature. There's, for those who are interested, like some kind of hands-on type of thing in machine learning, just to, you know, like rainy weekends, you don't want to go out and you want to play with something. There's like this playground TensorFlow. It's just a playground. So here's a neural network, and here's a problem. So the problem is very simple. So you have orange dots and blue dots, and you want to find a separation between them, a classifier for that, who can separate blue dots from orange dots. And there are different ones, like this problem over here. It's a bit more tricky. This one, it's kind of simple. This one, a bit more tricky, and so on. And the funny thing is you can add more inputs if you want, or less inputs. You have a neural network with these layers. You can add layers or remove layers as well over here. And you can add more layers, less layers, etc. You can play with a lot of things on the top, and you can change the problem to regression. So it's going to be a little bit different. You just press here to play, and then the system is learning. And it didn't took so long for it to learn how to separate blue dots from orange dots using this architecture over here. And if you press the mouse, you discover what the network is doing. So every neuron is kind of dealing with a part of the input space. And these neurons over here, they are kind of combining the previous neurons to separate them. It's kind of fun. And you can think about, okay, if I remove one neuron over here, what happens? Is it going to still work or not going to work? Yeah, still works. If I reduce now to just one neuron, that's a good way for you to understand a little bit more about accuracy and things like that. So accuracy depends a lot on the model capacity and some other elements. But you can play a little bit about this. Good. So briefly, key components of AI assessment. So AI assessment focuses on evaluating an automated decision-making system, mainly from a robustness, fairness, and explainability point of view. Of course, there are other points of view, but I guess these are the three main ones because that's where we have most of the tools for it. The goals of AI assessment, or algorithm impact assessment, would you prefer, is set the boundaries, usage, and shelf life of a system, build trust between the stakeholders of a system, and it's like the entry point to hold the system's creator accountable of the results of decision making. So that's the goal we are trying to achieve: usage, shelf life, create trust, and also accountability for the people. There are other areas of AI assessment like transparency, accountability, privacy, and so on. We're not going to touch on them today because we don't have much time for them. In a nutshell, robustness is systems should be safe and secure, not vulnerable to tampering or compromise of the data they are trained on. And I guess a key example of transparency, of robustness is the. Is my mouse over there? No, it's not. Oops, sorry. You have to put a pen. Laser pointer. Okay, it's not. So one of the key examples is the Microsoft Today, which we discussed earlier before. And just 24 hours online has to put down because it suffers some adversarial attacks. And that's a nice area of research these days, adversarial attacks. And if they have stress tested the model, putting some trolls to attack it, then we probably would discover this before putting online. Fairness. Systems should use training data and models that are free of bias to avoid unfair treatment of certain groups. And I guess Compass is the corner case for that. And explainability is systems should provide decisions or suggestions that can be understood by the users and developers. And I think for those who created Compass, if they have an interface, with nice UX for explainability, I think that would have been clear for them that the system had some problems in the first place. Because when you start to see the decisions being made for every individual, you start to see that race was playing some game they could have just shut down. So in a way, fairness and explainability tends to, in a way, work hand in hand. Because then for explainability, you can discover that something is going on, like in the case of the decision tree, for instance. Number of siblings popping up. It's like, we need to think more about it instead of just saying, let's roll out and see how it goes. Yeah. Assessment versus modeling. And going back to your point, which is from an assessment point of view, that's where fairness, explainability, and robustness kicks in. So in the data, how do you collect data and whom you're collecting data and which features you're collecting? You need to think about the fairness angle on that. How you are pre-processing data and engineering the data, that's where the explainability comes in. During model selection, how you're doing model selection and how you're stress testing the model, that's robustness comes in. And during the post-processing reporting, which systems you're putting in place so that the algorithms are more fair and they're also explainable. And finally, during the productionizing and deploying, how you are keeping these values and things going on when the system is actually on the fly working out there. That's the assessment angle. And there's the by design angle, which is you try to ensure that during those steps, by design, the systems are more explainable, more fair, and more robust. You can make the system more robust and fair, maybe even more explainable too. I should forget explainability here. During the pre-processing step. For instance, what your work with, for the recruitment case, you oversampling some of the classes or some of the genders in your case was you're manipulating the fairness into the data aspect. So people would call pre-processing step. You could also have encouraged the model to be more fair during its predictions during the model selection or the in-processing step. So you put some kind of penalty in how the model is behaving so that its prediction becomes more aligned across groups or across individuals. And you can also fix things. Unfortunately, you can always fix things on the post-processing and reporting moment, which is, okay, the system is there. I don't want to speak with the data scientists. I don't know what they're doing. I'm going to try to, when they come up with a prediction, I'm just going to change it slightly because I know that they're going to do something strange happening there. Which brings me to another canvas, which is the canvas you have on top of your desk. And it's a canvas we developed, me and Zainab, and it's the AI assessment canvas. It's not complete, of course, and you can give feedback. We are looking for feedback. And the idea is you give the first canvas to the data scientist so you can understand the model. Now I give the second canvas that I said, have you thought about these things when you were developing your model? And the idea is you move from some kind of value-centric approach to a more trust-centric or safety-centric approach. I'm not going to discuss the canvas on details. I don't have much time for that. In the slides on Zenodo, there's an appendix on these slides which discuss every box of the canvas in details. and you can give feedback. And if you want to participate on doing the development of this canvas, I'm very happy to have more feedback. And we're probably going to write a blog. If you're interested to participate in the blog, just give a shout, and we're going to incorporate you and your work together. But the main key thing on this canvas is how we reframe the discussion. Instead of thinking about delivering value, we want to deliver trust and safety. And if you have both canvas, I think in the end it's like a pedagogical tool that you can use for the data science for him to reflect about, oh, I didn't thought about these questions before when I was building my model. And I keep kind of banging this thing because a lot of data science who are out there, they're kind of somehow in my generation or even coming out of the uni right now, and they didn't got the education. So these are the kind of things you should try to put in front of them so they can learn and build on. Okay. So finally, I'm gonna dig deep, not too deep, but dig deep. Maybe another day, another time, we can do a full session on this. But let's talk about explainability. And explainability is the least mathematical of all the three pillars, the most subjective one, but in a way, it's the one which I think most of us agree what would be a good explanation for things and what would be a bad explanation for things. Fairness is the most contentious one. We have solutions, we have tools, but we cannot even agree on what should be a fair system or unfair system, what sort of mathematical definition we're going to use for that. But explainability, I think we pretty much agree when something is not explainable or explainable. So I'm going to focus on what do we mean by an explainable decision, and then I'll try to use the framework that Zainab has outlined before and try to just give you an idea about, for every step of the framework, what do we mean in terms of principles of something being explainable, not explainable, legal basis, different types of explainability, technological solutions, and a checklist. So one of the handouts is a checklist for explainability. It's like a table, and it's also in the Zenodo website, so you can download this too, even the canvas too, and you can use this checklist and give to the data scientist and say, can you fill these boxes for me? So just to see if you're doing your work properly. So what do we mean by an explainable decision? So we start with a cat, always a cat and a dog. This kind of examples we use all the time. Even though we do a lot of more things than cats and dogs, but I think the example we mostly use are cats and dogs. And then you have a neural network, and we discussed it before. You can just ask the network, like, what is in the image? And the network would say, this is a cat. You just ask it what is in the image. And that's probably a good answer for you. Then you can ask the network, okay, this is a cat, but why do you think this is a cat? And that's probably you need to come up with an explanation. So in the end, the model answers you given the question you have posed to him. So you just ask what, here's an answer. Why? Oh, this is a cat because it has fur, whiskers, and claws. It has these features. So some cat ears. So that's a more explainable decision. Maybe it's not 100%, but it's way better than just saying this is a cat. In healthcare, there's this nice website called Predict, and I can show you maybe later on. Predict is a system for NHS for breast cancer. And for those of you who are interested to know, in case you have a breast cancer or something related, you can go to this system and you can input some values about your treatment or about the diagnosis you received. And the system will come up with you with a full explanation of your survival rates, what kind of treatment you should follow, not follow, and so on. It's quite a good one. Yeah, it's...
Don't do it if you have a strong nurse.
Yeah. Okay.
And
That's true.
the false positives are an unresolved issue with automated
Yeah.
diagnostic
Yeah.
tools.
Yeah. And in finance, instead of just say your loan was rejected, they can give you an idea of why your loan was rejected. And sometimes because you didn't have much money on your checking account, or you didn't bank with this bank for quite a good deal more of years. So it would be good to know a little bit of what's going on. There are different types of explanations. So some explanations are kind of counterfactual. So if you were this person with this characteristic, we would give you, or they are sometimes, like in this case, the case of the cat, which is we give you some features of why we think you didn't get the decision. Um, that's where explanation becomes subjective because it depends on the application, depends on who are going to receive the explanation. The technical literacy of the people is very important. Some people are more technically literate, some people are less technically literate. So you need to think about all these elements. In an AI standpoint, there's this GDPR and the right to an explanation. Um, there's a lot of debate. I think it's probably more academic debate, to be honest, which does the system user really have a right to an explanation or not? And it's quite a debatable thing because they have the right in principle, but what type of explanation you're going to give to them, that's where it becomes fuzzy. So I still don't know the exact answer. People are still debating these things, but because it's a very new regulation. What we would hopefully have is we have the words. We try to capture the word in terms of a data set, like a tabular form, and then we build some black box model. And then using this black box, we would like to extract some way to interpret it, and then give to the humans. That would be the flow of explainability in the best case. Sometimes we don't need to do black box, sometimes we can do glass box model. It's not a problem. And we can do things by design who are interpretable. The problem is, in most cases, the most interpretable model, like a monotonic decision boundary, which, if you increase this value and increase this value, it's more likely you get a credit, it's more unlikely you get a credit. It's not as good as something very non-monotonic. So that's how a neural net would be, like in the case I showed you before. And unfortunately, there is a trade-off between explainability and accuracy, which is the same trade-off we have in fairness and accuracy. So this fairness and explainability are affecting robustness in a way. At the same time, robustness is affecting both. So how can we orchestrate all these things? It's a big challenge. And right now, who's doing these things is a data scientist working his computer, trying to get a model out of that. There's no basis or regulation. It's really like, oh, okay, if you think it's fine, it's fine. If you don't think it's fine, okay, we should change the model. And so there's the model specific ones, which let me just do it in my model. This one was over here, which is the by design type of explainability, which goes back to that point. And then when you have by design explainability, then you can have a global type of explainability or local type of explainability. Global would be like that decision tree I showed in the beginning for the Titanic dataset. That would apply regardless of the person who is going through the decision process. That will apply for the whole population in a way. And there's the local one, which is depends on you. So Amazon.com recommended you these books because you searched things that you like, or you like things that look similar to these ones. So there's an explanation that is for you as a client, as an individual, and there's an explanation which is for a group or a population. I tend to think that for the end user, this is more useful, but sometimes you don't want to open these things to the end user because you can suffer some adversarial attacks after that. And I think for for debugging purposes and for knowledge discovery, this tends to be more useful for the people who are involved in the process. So global explanations are for the developers of the system, and local explanation tends to be for the end user of the thing. And then you have model agnostic. And model agnostic is whatever the black box you are using, we can come up with techniques that can uncover which features and which characteristics of your model are more key. And here's the random forest for the Titanic dataset. Gender is very important. So still females are classified as survival most of the time. But class, which class you are in the ship is very, very important. Yeah. And you can see that siblings is like very less important right now because class comes in that moment. If you have global level, is this way. Local level is our case for the low one, the rejection of your low one. The key question is, if you are having to assess someone, if you cannot do this by design, I think probably model agnostic and then asking for some local and global explanation is key things, and you can do. And the good thing is there's tools available. There are some techniques, which I'm going to show you some the next slide, but there are tools available, and people can use these tools to build explanations. So there's no more excuse for not providing at least some explanation. I'll not say 100% good explanation, but some explanation. If you're not doing it, it's because, I don't know, that's not part of your work, or a little bit too lame, depending on, or you are kind of hiding away something and then you don't want to show it to the outside world. There's two views right now, which is there's techniques and why you're not using them, and why you're using this fancy model instead of now trying to use some technique, very simple ones, to investigate what your model is doing. Okay. There's some technical solutions for explainability, and here are some examples: the feature importance chart, and there's the partial dependency plot, and I think some of you have seen this chart before. Like when you increase the age of the individuals, the probability of surviving goes down in the Titanic problem. If your fare was high, the probability of surviving increases. So that's an explanation that you can give. And there's this local interpretable model agnostic explanations, which is okay, here's an image. Why you're thinking there is an electric guitar in the image, and the system tells you because of this part in the image. And why do you think there's a Labrador? Oh, because of this part of the image, and so on. So there is techniques and tools that you can use to explain decisions, even in terms of images, which tends to be quite complicated compared to just a row in a data set that you can use. And if you're not using, is because you didn't want to bake in as part of your deliverable when you start your project. Finally, the checklist, which you can find on top of your tables. Some questions that you can put in a checklist is, did you design the AI system with interpretability in mind from the start? It's a question you can pose. Another question is, did you research and try to use the simplest and most interpretable model possible for the application in question? That's a very important question. And I think all the data science kind of do this in a way. You have to build a baseline first. But these are questions that you need to reason and think about. Okay. Here are some papers and books. There's legislation over there. And if you want other good online resources about the topic and tools available on the internet, you can just access this link. And there's this nice XKCD, which is like a physician speaking with someone from another area. Say, oh, you're trying to predict the behavior of complicated system. Just model it as a simple object, and then add some secondary terms to account for complications I just thought of. So now I'm going to talk about fairness, and I'm just going to try to go down to the topics. And I think we have seen this before, which is the when a decision is not fair. So facial recognition, that's a big topic, and because you don't have much labels, from some classes, then you end up with system that cannot recognize faces from some gender and races, particularly in the intersection. And recruitment, in particular, for instance, this case, Facebook. Facebook tends to target based on gender, based on neighborhood, based on some other attributes, what type of job they would like recommend to someone. And then if you are a man, you get jobs like lumber, AI, I don't know what's AI. Maybe for a very artificial intelligence, probably, yeah, okay.
You know what's AI.
Fair enough. Taxi, lawyer, and so on. And when you're a female, I didn't want to show, but it's basically nurse and some other topics like that. It's very fun. It's fun. The principles of fairness, in a way, it's being always the humanity, if you think about it. Like if you go back to the old age of humanity, it's always being out there. And I think in the UK, in a way, it started with the Magna Carta, the first charter for, okay, here are the barons. We don't want to be treated more like peasants, like the other peasants. We want to be treated more equally by the king. And we are issuing this charter saying, okay, we are going to try to control a little bit of your power. Of course, Magna Carta was just for a small subset of people, was not for everybody. And then gradually, this thing starts to go to more people and embrace all the different regions of the world. And I think the most overarching one was the UN, Universal Declaration of Human Rights, which came after the Second World War. And after that, then there is more, these principles are starting to become more legislation at the local level. And AI, fairness, it has two concepts. One is the concepts of fairness being a substantive concept, which is to try to treat different groups in a substantive, equal way. And you also try to create procedures that these two groups would face. So you have a substantive way, which is about resources, and procedure, which is about techniques that you are applying to these groups. And the legal basis for fairness, there's a lot of legislation around, and most countries, I guess, when they have a constitution, fairness is there as a key principle. And it's like in France, in Germany, and Brazil, and I think in Turkey, and some other countries around the world, it's over there. In AI standpoint, you can find fairness more as a principle, I guess, not still as a legislation, unfortunately. You can get some principles on the IEEE ethically aligned design. And the one that I really like a lot is the European Commission Ethics Guideline for Trustworthy AI. They really did a very good job on mapping the key elements for fairness, for robustness, and for explainability. They have everything there. The checklist which I give to you is something that I took from there. So everything's there. When you try to come up with a mathematical definition of fairness, you end up having to think about data, think about model, and think about outcomes. And we discussed this before. The main challenge is the data, which has been tainted across time. And in a way, when you design the system, which is unfair, and you didn't thought about it before, it just perpetuates. And it creates more samples that replicates the previous one and just reinforce the principles. Sometimes you don't have features for some groups. And that's very common when you want to do research in very rough neighborhoods, like in favelas in Brazil. It's difficult to go there and collect data because people don't tend to have address in these places. You just know the neighborhood, you just know where the people are living, but you don't have an exact data point for them compared to the nice flats in Copacabana Bay, which the data there is more abundant, it's easy to analyze. And you have the proxies problem, which is the color and the shape or the neighborhood you live, and so on. When you think about The mathematical view is you need to think about individual and group fairness, and I think Zeynep has talked about individual fairness and group fairness. And there's really a mathematical expression for everything. So individual fairness is very simple. F of x here is the decision made by the system to you. And all these points over here are people who looks like you and how the system has behavior for those systems. If the decision was equal to you, this thing would be 0 and the consistency would be 1. Okay? If they're too far apart, then the consistency will be close to 0. So it's not consistent for an individual level. Group level is a bit more complicated, and I'm just going to show you why it's a bit more complicated, because you need to think about which type of definition of group fairness you want to use. Do you want a fairness by outcome or by opportunity? And that's where the data scientists don't want to discuss. Like, okay, can you give me the formula and I'm just going to implement that and then just move on? When you talk about opportunity, you're talking about, okay, everybody that has applied for this job or to this recruitment process, they had the same opportunity, so I just can use the features as a good predictors for that. And I just need to make sure that my model is not biased towards a group or flagging a lot of false positives towards a group compared to another one. The outcome is I'm going to try to treat different groups the same. So whatever the prediction of my model, I'll try to get the same distribution across groups. So outcome is way more stricter compared to opportunity, because opportunity is about performance of your model across groups, unprivileged and privileged groups. Sometimes unprivileged groups can be male or young people. I'll give an example. Compass, for instance. Male is the unprivileged group there, because the privileged group is female. Female tends to have a better treatment in terms of these models compared to males. And in Compass, you try to get a equality of opportunity there to try to minimize the false positive that you have a way more for men than for female. And in Compass, the race is the black and white. Yeah. There's a tree. And it's like a decision tree that you can use to identify which definition you should go for. I showed you just 2 definitions, but you can have way more. So that's why it's a difficult topic and still up to debate in most cases. There are some techniques you can use to alleviate bias during your modeling. You can alleviate bias or unfair decision making in the pre-processing step, in the in-processing step, or in the post-processing step. And I'm just going to show you an example. So this first one here is alleviating bias in the pre-processing step. So you have your model, so you have your data, and when you break down your data into 2 groups, so let's say group blue and group orange, you are trying to remove this impact that this scoring is happening across these groups. And then usually, if you are coming up with some type of new IQ test or some type of new creativity assessment, that happens a lot when you break down by gender. So you have these 2 gender groups, and let's say males and females, and you say, okay, there's a clear difference there. I don't want this difference to appear because I don't think gender has a key factor to explain why someone is more creative than another one. And then you basically tries to subtract the mean from this distribution so they become more aligned. That's a way you can correct the features before you move on. Another way is to do this in the model level, during the in-processing. So here is a nice decision surface, and going back to our example in TensorFlow during those plays. So here's a cloud of points, red points and green points. If you just let your model completely unfettered in terms of fairness, that will be the decision boundary. So almost a perfect prediction from your model. And when you start to take into account fairness in terms of a constraints, so if you plot not only if the dot is red or the dot is green, but also what kind of group this dot belongs to, and if you do this as a cross and as a dot, and I think that's probably difficult to see, but you're basically saying not only the dot has a color, but also they have a format. So they could be this, they could be that, or they could be this, they could be that. So they have only a group and a class. If you try to take into account that, the model has lower accuracy, but they are way more fair compared to another one. And then you can mitigate that into the modeling process. So again, going back to the discussion we had before, the techniques are there, the tools are available, you can do that, or you can ask data science to do that for you. So there's no more excuse, but you need to think about what type of definition and what sort of systems you want to have. There's a checklist, which is also on top of your table, that you can use to do AI or algorithmic impact assessment. So there's some papers, online resources, and that's why I told you most of the research in fairness has been over the last 7-8 years. So people just thought in the beginning that was like, oh, some people researching fairness, that's fun. And then suddenly, this is massive amount of publications over the last 2-3 years. And to be honest with you, any conference on artificial intelligence these days has a workshop, has 2 or 3 sessions, and has 3 or 4 panelists on this topic. It's like really massive now. Just finishing, robustness. So we have seen these examples before. Microsoft Stay, facial recognition not working. And there's this example over here, which is you take an original image of a benign tumor, and you apply a small amount of noise to the image, which is kind of imperceptible for a human. And the system says, now the tumor is malignant instead of being benign, as it used to be. And you can think about like, well, what's going on? It's still the same image from a human perspective. We can see that's the same image because, I don't know, maybe during evolutionary process, our brains and the filters attached to it was able to filter any particular amount of noise, and you can still recover the original image. But a computer, if it's not trained properly, cannot do it well. And it's just a small amount can render something benign as malign. So in terms of principles, robustness falls into the principle of prevention of harm, and it has a lot of literature behind it. And you can also find it in the UN Universal Declaration of Human Rights. It's also there. So in terms of principle that we are following when you're thinking about robustness, is over there. The problem is the legislation. And the good thing about robustness is there's a lot of legislation out there. And most of the legal basis is established by an interaction between regulatory agencies, professional associations, trade groups, and they think about the standards, the code of conduct, and so on. And in finance, we have the FCA, the UK, and the Financial Stability Boards, and the British Bank Association, and we can think about the Bank of England as well playing a role, and the Treasury. So all these agents, they sit together and they think about what the rules are. And it's very sector-driven, which is quite nice because robustness is a question about what's the application in the end. It cannot be something broad. If you want to find something about AI, particularly, you have to look into the European Commission's ethics guideline for trustworthy AI and the IEEE one. When we think about the mathematical definition, we can think about 4 aspects of robustness. first aspect is the resilience to attack and security. And we discussed this before, but Microsoft today was not scoring very high in terms of resilience to attack. What is the fallback plan? And our friend from the Department of Work and Pension said the fallback plan is there's a human who comes in and do the intervention. That's good. Accuracy, very important. And then we got the in the beginning when I showed you the staggeringly inaccurate facial recognition. That's a big thing. You try to have a system which can make correct judgments instead of just having a system that comes up with prediction that doesn't make any sense to reality. And you need to think about what you have in place, and I think there's way more computer science point of view that can make the system reliable and reproducible. So if you come up with a new machine learning model, how can you show the steps you have come up with to design this system and to reproduce this system in case we need to do it afterwards in some other domain. We can map each criteria, accuracy, resilience to attack, and so on, into mathematical or technical concepts. So accuracy can be mapped to something called expected generalization performance, which is basically the question, in general, on average, the algorithm works. The question of resilience to attack can be mapped to adversarial robustness, fallback plan, and general safety to formal verification. And reliability and reproducibility can be put into continuous integration. And each one of these mathematical and technical concepts, there is a formula for them. So when we started with interpretability or explainability in the beginning, we had no maths. There's some maths, of course, happening in the background, but there's not a good definition. And then we start to become more mathematical as we went to fairness, and now quite a good ideas about what we mean by robust or what we don't mean by robust. And I feel that the other areas are kind of moving gradually towards this more, we have a good idea about what we mean by something fair or something explainable and not explainable. But I think it gets over time. I'm just going to show you some examples of what we mean by these mathematical formulas, which are a lot of approximations. When we think about expected generalization performance, we can use technical solutions like cross-validation, covariance penalty, and so on. For robustness, adversarial robustness, we can use evasion attacks, defense techniques. Verification, formal verification is very hard. You need to have an idea about what's the correct solution to that problem. So if you're modeling a physical system, it would be good for you to have the physical model. And if you're trying to approximate that physical model using some model, you need to see whether this model respects the physical laws behind that system. And reliability and reproducibility, I think, is the most of all advanced. We have so much tools available, and most of them are for free. GitHub is an example. When you're a researcher, it's for free. When you're working in a company, it's not too expensive to use. You can use Bitbucket via Mercurial and so on. If you want to reproduce your analysis, you can use Binder or Docker, etc. If you want to do testing, you can use Travis, Scrutinizer, etc. So there's tools available. You can just put this stuff together and work on. Just to give you an example, what do I mean by these techniques? One is, how do you measure generalization performance? You can use something called cross-validation, some of you are aware of. You have your data set, which is this massive block over here. You just split the data set with the data that you are going to give your model to learn, to train. And this other bit of the data that you're going to use for your model to validate itself, to assess the performance. You do this 6 times. You get the accuracy of a model for that holdout set, and you average that. That's roughly the generalization performance that you expect that your model is going to deliver in real life. And that's another type of thing that you can do, which is you start with an image, like a panda image. You add some bit amount of noise there, and then the system says, oh, it's not a panda anymore. Now it's a gibbon. So that's a way which you can assess whether your model is robust, not robust, etc. So finally, there's again, checklist on top of your desk, and a lot of questions that you can pose to the data scientist about how robust is the system he's developing or not. Just some papers to read and some online resources that you can find. There's a nice XKCD as well. This is your machine learning system. Yep, you pull the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? You just steer the pile until they start looking right. And that's pretty much how you shouldn't develop a robust system. But I think that's it from my side. And thank you all very much for staying along.